All right. Welcome everybody to week 2 of the classes. So we're gonna talk about microarchitecture today. If my screen starts to work. Hmm. Sorry for the delay. Got it. Okay. So today we're going to talk about microarchitecture. This is an important topic that uh, we're going to use a lot, and one of the most important kind of part of this class. Your first project is going to be also about this lecture and the next lecture that we're going to cover next on Thursday. A few announcements. Let me see if my okay. So homework 1 obviously is out, right? It's due on this Thursday. Yeah. The mic for some reason doesn't work well, but the mic is on, but it's not projecting well. I don't know why. But I'll try to speak a little bit louder. Uh, so homework 1 is out. It's due this Thursday. One thing to notice is that, instead of running documents, I usually share a Google Doc. So we sometimes see like the typo or error or confusion, and we try to kind of fix them, right? We usually show them in red. This time we didn't, but from the next time, if anything changes on the homework, we'll show it in a red font. So if you see something that is like changing, we'll see that there. Typically, these changes because there are some errors or there's some clarification needed. For those of you who already kind of like submit your homework, you don't need to worry about the changes, essentially, because as I said before, this is more of like a completion. So it's more of you try to attempt to answer the questions rather than anything else. So it's okay that if you answer the previous version. One thing you have to pay attention to is like why we make those changes and what happens and so on and so forth. So pay attention to that. But if, for example, we change something, you don't need to go back and resubmit. Okay? That's one. The second thing is that I see on Campus Fire lots of posts, which is great. Two things I want you to do. One is make sure to read all the posts before you're making a new post. Second thing is that there's also possibility that someone answered the question incorrectly. We typically don't delete those answers. The reason for it is that usually wrong answer is actually not a bad thing. It's actually great because many people might have the same misunderstanding about the concept. So we let it be there, but we typically answer we reply to that comment and kind of provide the correct answer. So one thing I want you to pay attention to is when you're reading the post, make sure that you read all the replies and pay attention to kind of the whole discussion, the whole timeline, because sometimes you see something that may not be completely accurate, but the answer below it is, okay? Sometimes I also edit the post if it also cause confusion. So if you make a post or comment and see that it changed, or I put something, it's either me or one of the TAs have made those changes, okay? So, and again, we try to keep everything there so that you can also see the mistakes that might happen. I'm being scammed. All right, sorry about that. So yeah, pay attention to that on campus wire as well, okay? One more thing I wanted to say, which I forgot, but anyway. Any questions before we get started? All right. So last time we talked about ISA, and then like very last slides that I covered was how to implement an ISA. And we said that the implementation of an ISA is what we call microarchitecture. Essentially, we said this at the beginning of the class in week 0 as well, that given an ISA, you can have different implementations, okay? So essentially, the underlying hardware implementation is separate from the ISA itself. There is no like, oh, this is RISC-V, this is the instructions. There's only one way to implement these instructions. There are actually multiple ways. And as we will discuss today and next week and next lecture and next week, you will see that there are essentially computer architecture is all about this design decisions. There's no one particular right or wrong answer. There are, you know, sequence of lists and things that you can do, and you choose between them. How do you choose between them? You choose different metrics such as performance or power or the cost of adding this feature and that feature. So there are these kind of trade-offs that you constantly, you know, considering, and based on that, making a decision. Okay. So just keep in mind that there could be same ISA but different microarchitectures. Okay. We're gonna particularly talk about a very specific microarchitecture in this class, and that what you need to also implement in your project. But keep in mind that there are other ways of implementing the same ISA. Okay. And then, as I said, the main goal is efficiency. So we're gonna try to, first of all, try to optimize the performance as much as we can. But if, for example, optimizing performance would require a lot of cost, and I'm gonna define what cost means, then we go with not optimizing the performance. So we don't want to optimize performance at all costs. Sometimes we need to balance it with some other factors in the system. Okay? That's why we don't say performance only, we say efficiency. All right? So what is the strategy that we're going to use in order to implement an ISA? Okay? The strategy we're going to do is some form of this two-part design, which has what we call a controller, and then it has a data path. Okay? So the blue part is what we call a data path, and the red part is what we call a controller. So essentially, a microarchitecture is this two-unit thing that has a data path and a controller. Controller is essentially controlling the data flow of the instruction through the data path. And data path is actually the units that we're going to use in order to execute various different things in an instruction. So for example, we need to fetch an instruction, we need to decode it, we need to execute it, and so on and so forth. Okay? So this would be essentially your CPU. Each computer system also has obviously a memory. So the memory kind of goes hand in hand with your CPU, but generally memory is not part of your CPU, is not part of your microarchitecture. So essentially we are designing these two main parts, the controller and the data path. And as you can see, the data path has a bunch of different things. It has PC and instruction register and register file and ALU and so on and so forth. So we're going to break this down. And as you can see, there are lots of control signals and conditions that are going back and forth between the controller and the data path. This is how we're going to basically control this. Of course, the controller also needs to talk to the main memory for some instructions and some control signals. So we're going to talk about that as well. And then finally, the main interface between the memory and the CPU is the address and data, right? So we provide the address, we read the data, or we can also provide the data if this is, let's say, a store instruction, right? Okay. And as I said, this is what we're going to actually kind of show you part of it this lecture, part of it next lecture, and see if we need next week as well. This blue parts are what we call the controller. So as you can see, controller is mainly just one big unit here. There is a small ALU controller as well. And the rest is just these control signals that goes through various different parts of the data path to control the flow. Think about this as kind of like valves. So we kind of open a valve or close a valve so that the data flow can go through different pipes. That's literally how the controller works. And these black signals and this black wires and all, these are all part of your data path. Okay, so this is kind of the notation that we're going to use in this class. Okay. All right, so let's talk about how do we design this. And we're going to design this step by step, starting from left to right. So essentially, the instruction is going to execute starting from here, and we go kind of like the flow, the timeline of the instruction is kind of from left to right. So we're going to gradually add this each individual units and the connection between the units, and we're going to describe why we're making this decisions. Okay? To understand that, we need to understand the life cycle of an instruction. What happens for an instruction? What is executing an instruction means? Okay? So it's multiple steps involved. The very first step for executing any instruction is what we call fetching the instruction. So remember that I told you that instruction is stored in the instruction memory. So the CPU needs to go to the memory and bring that instruction into the CPU. We call this process fetching. Okay? Then when we have fetched the instruction, so now we have one instruction inside the CPU. Now we need to understand what this instruction is and what are the operands for that instruction is. Remember that each instruction has two main parts, commands and operands, right? So we need to basically load the operands. And if you remember, I told you that operands are either registers, immediates, or memory, right? So depending on which one do we have, we might have multiple of them or just one of them, we need to do the proper actions, right? So for example, we need to access our register file, and remember, register file was the place that all of our registers were stored. We need to either access the data memory to bring the data from the memory if the operand is from the memory, or we need to somehow load the immediates. And if you remember, immediate sometimes needs to be sign extended. Sometimes we had this weird way of putting like various bits as different various places, so we need to kind of like shift them back in the right order. And those kind of things we need to do for the immediates as well, okay? Then we have the operands, and we know the instruction. Now we need to actually execute the instructions, okay? So if you remember, I told you that there are three types of instructions that we have. We have ALU operation, arithmetic operations. We have what we call the memory or data movement-based operations, and then we had control flow operations, right? So for each one, we need to do different operations. We need to do different things. For arithmetic, we need to know which type of arithmetic it was. Was it a sub or an add or ORI, and so on and so forth. And remember, we had the opcode, and we had the func3 and func7 to decide that, right? For the data movement, again, we might have a load or store. Each load or store also had different types, like you had the store bytes, or you have store half word, or you had store word. For load, you had also signed and unsigned word. So we need to also define that. And finally, for control flow, we had different types of jumps. So we need to find the address, and we need to jump. There's also additional check that we need to make for the branches to check the condition first and then jump, right? So there's these two additional things that we need to do, okay? Once we do all those things, then the next step would be, where should we store the results, right? So we did something. Now we need to kind of update our state so that we can go to the next state. If we don't update it, then it doesn't matter what we do if we don't have anything saved. So we either usually store the results into the register file, right? So there is a destination registers that we talked about, or we need to store things into the memory, right? Or in some cases, we need to update the PC. So if this is a control flow instructions, we need to also write into the PC, right? And then once we do that, then we update the PC, and then go to the next instruction. Remember that typically the next PC is just PC plus 4 because we always go linearly, unless we need to jump over some instructions. We either jump forward or jump backward. And then if it's a branch, we need to first check the condition. If the condition is true, then we will jump, right? So we update the PC, and we repeat this process for the next instruction. So essentially here, we jump back to step 1. We fetch the new instruction. We do all this process one more time, and then go to the next instruction and next instruction and next instruction, okay? So this is the timeline that we are following. From the rest of this lecture, I'm going to actually show you each of these steps one by one, and I'm going to show you how we actually implement these things, okay? Any questions so far? Great. All right. So how do we do the fetching? I told you that the very first thing we need to do is that we need to provide the address to the instruction memory, and we will read the data from the instruction memory. For now, we're gonna assume that there are two separate memories. One is we call instruction memory, and the other one we call data memory. But in reality, both of them are part of the same unified memory, okay? So essentially, there's no difference between reading data or memory or address, instruction or data. The only difference is the address that we provide. If the address that we provide points to an instruction, we read an instruction. If the address that we provide reads a data, we read the data, right? So that's the only difference. But for data paths, in order to make things a lot nicer and cleaner, we're going to differentiate between an instruction memory and data memory, okay? So the CPU provides the address. This is the address that we need. Address. And then we're going to get the instruction. And remember, instructions are 32 bits, right? So it's 31:0. So we're going to read the whole 32 bits together when we are reading an instruction. And remember, that was 4 consecutive lines in the memory, because memory, including the instruction memory, was byte addressable, all right? And we do little endian, which means that the lowest byte is the lowest address. The highest byte is the highest address, okay? So 2 things to remember. We typically use this notation to show that the value that we are reading is 32 bits or n bit, okay? So if you see a line and then kind of like a diagonal line and a number here, it means that we are reading this many bits, okay? So we're not going to show you 32 lines. We're going to do 1 line and show the number on top of it, okay? So this means that this line is 32 bits, in fact, okay? So you may also wonder that how the reading process works. So this is like a quick detour on logic design. This is what you've learned in your M51 or M16. And again, Tia is probably gonna like quickly go over kind of the logic reading, like sequential and combinational logic and all. But let me quickly talk about this as well. So if you remember in your logic design class, you had essentially 2 elements in your logic. You have what we call combinational elements, and you have what we call sequential elements, okay? Combinational elements typically operates on the data. It's outputs on a number, and it's not synchronized with any sort of a clock or something. Sequential is those elements that have some form of a memory, so you can store some information inside the logic unit. Sequential, logic is typically shown as a flip-flop or a register. When we say a register, we typically refer to the sequential logic, right? Register at very bare bone register has kind of 2 inputs. It has the data inputs, and it has a clock input, and it has an output we typically show as a Q. Registers are typically edge trigger, which means that once either the positive edge or negative edge of the clock comes, the data from D will be sampled into Q, right? So this is kind of the timeline that I'm showing you here. The clock comes, okay? So I'm providing some data here, and the Q is kind of the output that I'm providing. The positive edge of the clock comes, and after some delays, this is not instant. There is some time between the time that the clock comes and the output is updated. So the data will be updated at this point, right? And this is what I'm showing here is at the positive edge of the clock. So this is sensitive to the pos edge, but you can design a register that is sensitive to the negative edge as well, okay? So for example, here again, the next positive edge comes. Whatever value that I'm providing here will be updated here. So for example, let's say here I have value 0. At this point, this value becomes 0. Now if I provide 1 here, at the positive edge of the clock, this value becomes 1, and so on and so forth, right? So the D becomes, like the Q becomes equal to D on the positive edge of the clock after some delay, okay? Um, and again, the internal design of this kind of registered flip-flop and what is this delay and how much this delay is and all those things is not going to be something that we're going to be worried about in this class, but I'm hoping that you understand the internals of this system as well in your prior classes. If you didn't, I think it's a good time for you to review that as well, okay? Registers typically also have what we call a write enable. This is a control signal to enable the write. So this one that I showed you here, always update Q based on the positive edge of the clock. So by default, you always write to the register when the pos edge comes, okay? But there are many instances that you don't want to write to a register every clock cycle. You want to be able to say that, okay, if the write enable is 1, is active, then write. If the write enable is not active, then don't write anything to the register, okay? This is very useful for our case when we're designing a register file, because not all the register needs to be updated every clock cycle. So only the destination register needs to be updated at one particular time. That's why we typically have what we call a write enable. We typically show it with like WE or just write. And what happens is that the difference between a register with a write enable and without a write enable is that my Q will be getting updated when the positive edge of the clock is coming, and when the write enable is active, is 1, okay? So in this case, we see the update here. But if the write enable is equal to 0 and the positive edge comes, nothing happens here. So the Q will not get updated, even though the pos edge comes and the data has changed, but nothing will update it on the Q, okay? Typically, write enable, if write enable is equal to 1 and then we write, we call this active high, which means that the register is active when the value is high, when the value is equal to 1, okay? If the register is active low, it means that write enable needs to be equal to 0 for this thing to be written, okay? By default, we typically assume active high, okay? But keep in mind that there's also active low, all right? So that's the difference between the two. All right. And then you can consider kind of the memory the register file as kind of an array of these registers, okay? So we can have, for example, a memory that has, you know, sequential logic. You can assume it as a 2D array of width and length, right? And each one becomes essentially a one register, okay? Your DRAM or your SRAM is not based on registers and flip-flop. They use a completely different technology that I'm going to talk about later. But your register file is essentially an array of this single bit registers that I showed you here. So each one bit is something like this, okay? So now the question is that, for example, if I want to read a register or write to a register, how should I do this, right? So how should I read this? The first thing you need to do is that you need to select a line, right? So you need to have a mechanism that if you provide the address and you want to read any of this, you need to first decide which of these lines should I choose, right? And typically, this is done by some form of a logic that we call a decoder, right? So the decoder essentially pick which line you want to select. Very simple example, consider that you have only 2 lines. So essentially, you only need 1 bit, either 0 or 1. If it's 1, you want to select this line. If it's 0, you select this line. If it's 1, you want to select this line. How do we do that? The simple thing you can do is a multiplexer, right? So you select between the output of the lines. So you put a multiplexer here. So let's say, for example, I have a 2 by 4 bit register file. So I have 2 registers, each one is 4 bit. Or I have a memory that is two memory lines, each one is 4 bit. And I want to read, okay? How can I read this? I essentially can connect all the lines to a multiplexer. and I have a selector and use the address as the selector to choose. In this case, if the address is equal to 0, I'm going to select this one. If the address is equal to 1, I'm going to select this one. If you don't remember how the multiplexer works, don't worry. Again, something that you may want to kind of check. But generally, multiplexer, we typically show it as kind of like something like this that has a selector and has two data. Typically, we have like 2-to-1 multiplexer, which means that we have two inputs and one output. So the way it works is that if selector is equal to 0, we will pick this line here. If the selector is equal to 1, then we will pick this line. Okay? This is how we're going to select between the two. And remember, in our data path, we're going to, as I told you, think about this as a valve that you're going to select which lines is connected to which line. This is going to be very, very handy in order to select which line is which. And then again, for reading memory, we're going to do the same thing. We're going to connect all the addresses into a big mux, and then we select which line do we want to select. And now you might wonder, okay, how do we select out of 4 lines? So if I have 4, how do we select this? Then your selector needs to be 2 bits, right? So if you want to select 1 out of 4, you need to have 2 different bits, where 0, 0 would be this one, 0, 1 would be this one, 1, 0 would be this one, and 1, 1 would be this one. How do we build that? We build this based on multiple selectors, on multiple multiplexers. And again, something that we're not going to be worried about in this course. We're going to abstract this away and just consider that there is this block called multiplexer that provide the selector and can choose one of the inputs from the inputs that is connected to that unit. Okay, that's all we're going to care about in this course. All right. So going back to reading memory, if I want to read anything, for example, I want to read the instruction memory. I provide the address. How do I select that particular line? I have a multiplexer in the end, which I'm not going to show in this class, but there will be a multiplexer in the end that selects which of those lines you're going to read from. Okay? There are other ways to do this. You can have a decoder, an encoder, and all those things. But for now, just to make things very simple, the selector is going to tell us which line we're going to pick. Okay? Questions so far? All right. Basic rudimentary stuff. So now the question is, are we using the exact same cells that we use for registers for DRAM and SRAM technology? And the answer to that is no. The reason for it is that there is a trade-off between the cost, the latency, and the area for storing. Okay? So we typically have 4 different types of technology for memory. We have what we call the registers, which is essentially either latch or flip-flops. These are very fast, but very expensive. Expensive, when I say expensive here, I mean the number of transistors, the area that it takes, okay? So in order to store one bit of register, you typically need tens of registers, okay? So storing 1 bit is a huge cost in terms of area. But the nice thing is that it's very quick. You can read data from a register within 1 clock cycle. Within nanosecond or picosecond latency, you can read things off of a register. Okay? So we typically use register files this way. So register files is this big bank of all these flip-flops sitting next to each other. Okay? Then we're going to have what we call an SRAM and a DRAM. Okay? SRAM is going to be used for your caches, and we're going to talk about caches later in the course. SRAM stands for static RAMs. It's usually a 6-transistor system, so it kind of like looks something like this. So it's kind of like the transistors are connected this way. And then there are 2 selector transistors here. So this is an SRAM. This is your VDD, and this is your ground. So SRAM looks like this. Typically, you have a 6 transistor that kind of connected this way. Again, the internal of an SRAM is not a concern for you in this class. But again, if you're interested, go and check it out. This is used for storing only 1 bit again. Okay, so this is only used for 1 bit. Uh, it's slightly better than a register file, which requires tens of bits, but it's much slower than a transistor than a flip-flop. So it typically takes uh, multiple cycles to read a bit from an SRAM. Okay. Then we have DRAM, and DRAM is really, really efficient. So DRAM only typically just needs one transistor and typically one like a big capacitor, and I can read a data from a DRAM with 1 bit. So I kind of like have 1 bit, 1 transistor equivalents for DRAM. But the problem with DRAM is 2 things. One is like significantly much slower than SRAM and register file to read the data. But it's really cheap. And then the second thing about DRAM is that you need to refresh DRAM because there is some form of a leakage and destroying the data when I'm reading it. Okay. So DRAM is what we use as what we call the main memory in our designs. Okay. And finally, we have disk. Disk is usually a completely different technology. It's based on usually a flash memory. There's also other technologies like magnetic junctions and so on and so forth. DRAM, you can actually store lots of bits in equivalent of 1 transistor. It's not really using any transistor anymore. It's using a completely different technology. But it's very, very cheap. You can store terabytes of data. But it's much, much slower compared to DRAM and SRAM. So we are talking about orders of magnitude. So this is like, if this is 1 cycle, this is typically tens of cycles. This is typically hundreds to thousands of cycles, typically thousands of cycles. And here we are talking about 100,000s of cycles. Okay? So this is the order of latency between these different technologies. Okay? But as we are moving down, we can store much more bits into a single cell. Okay? So the design of the memory, this is what we call memory hierarchy. And again, we're going to revisit this. It looks something like this, that at the top of this pyramid is your register file, which is very, very fast, but very, very small. Okay? And then at the bottom, you have your kind of like disk that is very, very slow, but extremely large. And then you have your DRAM and SRAM and all those things in between. Okay? You had a question there? Yes, yes. So the question is about the SRAM. How do we read a word from this? Yeah, you have, think about this as a 3D design that you have a bunch of this stacked together and then you read off. And then you actually, SRAM is really designed for reading things in volume. So there are lots of circuit techniques and analog techniques that we use in order to make this very fast. Yeah. So the question is why DRAM the data is destroyed? Because essentially the way that we store data in DRAM is we're storing charge in this capacitor, okay? So we store some charge in this capacitor. And what we do for reading is that, think about this as think about this as like a bucket with some charge. And think about this one as like a much bigger bucket that we kind of like, pre-fill it a little bit. Now, when we are reading, we are essentially connecting these two together. So we let this to flow here, okay? So essentially, by flowing this into here, we let this deplete if it's a 1 value. If it's 0, nothing happens because there's nothing to kind of like go. There might be actually, at some point, there might be some coming from here to here. But generally, the idea is that you let the fluid, the charge to deplete from your capacitor. That's why it's kind of basically destroying it. So the way that this works is that we let it read, and then we kind of replenish the charge again. So we refresh it each time that we read. We're going to actually talk about DRAMs later on in the second half of the class. So you're going to see more about this. All right. So this is, by the way, a complete detour of what we're going to talk about. But it's typically, I've seen that this is needed for people to understand. So as I said, there is a big trend in memory that if you start from register all the way to DRAM to disk, you start from smaller but faster to bigger but slower. And then again, and then another thing, another trend that you will see is that you start from more expensive and more power hungry, which means that your register file is really consuming a lot of power, to a disk that is very cheap and very, very power efficient. Okay? So that's why I cannot have like a really, really massive register file, because it consumes a lot of power that I cannot afford. And I already discussed why consuming a lot of power is a big challenge in designs. Right? And then, as I said, this is kind of like comes the idea of memory hierarchy. So the idea is that since I have these different kind of tools and these tiers, maybe I can try to have a data management, data movement strategy that if most of the time I use the register file, then I have this illusion that I have the biggest and fastest memory at the same time. So if I can somehow in the background move the data to the register file all the time at the right time, then I'm going to always just interfacing with the register file or interfacing with SRAM. Never need to go to the disk or the DRAM. But I need to have this very, very sophisticated data management strategy to do that. We're going to talk about how do we achieve that when we are talking about the main memory. But keep in mind that we typically have this. So most of my time, when I say my time, I mean the CPU time, is spent interacting with the register file and the memory and nothing else, and the SRAM and nothing else. So DRAM and this very rarely are visited in our designs. Okay? But as I said, we're going to talk about this in much more detail later in the class. I wanted to just give you a quick kind of rundown of the memory because that's much needed to understand the rest of this lecture. Okay? So going back to this is where we started. We said that we provide the reading address, and we're going to read the instruction. And as I said, for now, we're going to assume that this is a memory unit that has some form of an internal multiplexer that selects which line we're going to read. And as I said, each line essentially is 8-bit, right? So each horizontal line is 8-bit, and we have many of these lines in the memory depending on the size of my memory. Okay? So now the question is, and as I said, we're going to read 32 bits. Now the question is that how many bits do I need to provide here, right? Do I need to provide 32? Do I need to provide less? How many bits do I need to read the address? And by the way, we need to use the PC, and then PC is a register. That's why I'm showing it as this, right? So this is like a register that has a clock. Sometimes I show this clock here. Sometimes I don't show it. Just consider that this is a register. So I'm going to connect the PC because PC is where the addresses are pointing to, right? The instructions are being pointed to. So I'm going to connect the PC to the memory. But now the question is, how many bits of PC do I really need to read the address? Anyone wants to answer this question? Is it 32 or it should be less? And why? First of all, PC is 32-bit. That's already we know because it's just one register similar to other registers that we have. But do I need all the 32 bits to read the address? Does it depend? If it does, depends on what, and so on and so forth. Yeah. Exactly. So it depends on how many lines do I have here. All right. Essentially, log2 of this will give me the bits that I need to read the memory. If I provide more, we only take the lower bits for reading the memory. Okay. So this is typically what we do. Okay. So for example, if your memory is let's say 1 kilobyte, how many lines do I have? Anyone wants to answer this? Let's say my instruction memory is 1 kilobyte. How many lines do I have? Anyone? You want to answer again? Maybe you? Say it again. 2 to what? 256. How did you get that number? Okay, so you divide this by 4, and that's how you got this number, kind of. You divide it by 4 bytes, and that's how you got this number. So keep in mind, so again, let's go back. So we have 1 kilobyte memory, okay? I want to see how many lines do I have. The first question is, what's the width? The width is 1 byte. It's not 4 bytes. Again, don't be mistaken by the fact that we are reading 4 together. So each line is 1 byte. So if each line is 1 byte, how many lines I'm going to have? I'm going to have 1K lines, right? 1K lines I'm going to have because each line is 1 byte. My entire memory is 1 kilobyte, so I'm going to have 1,000 lines here, okay? Typically, we use this approximation that 1,000 is equal to 1,204, so we use this as 2 to the power of 10. So typically show this as 1Ki instead of 1K. So if I show you this way, that 1Ki bits, I mean 1K is equal to 1,224. So in other words, I have 2 to the power of 10 lines in this memory, okay? How many bits do I need for that? I need log 2 of 2 to the power of 10. I need 10 lines or 10 bits of memory to address this 1K byte memory. Does that make sense? So to repeat, I told you that if I have an instruction memory that has 1 kilobyte of data, how many addresses, how many bits for the addresses do I need? The way I calculate this is that I said that this is given. Always my memory is 1 byte, okay? So my width is always 1 byte. So I know for the fact that each line is 1 byte. So now the question is, how many lines do I have? So I divide 1 kilobyte to 1 byte. And this is how I get 1K here. So I have thousands lines. Another thing I told you is that we typically make this approximation that 1,000 is for us is 1,024, which means that it's equal to 2 to the power of 10. So I have 2 to the power of 10, approximately 2 to the power of 10 lines. How many bits do I need to address this? Log 2 of that is the number of bits I'm going to use, right? So if I have, for example, 8K bytes, how many lines do I need? How many bits? Anyone? Yeah, so it's just essentially 2 to the power of 13, and then log 2 of that, you need 13 bytes. And then so on and so forth. So if I tell you the size, that's how you quickly calculate how many bits do I need. Yeah. Say it again. 1 byte. Yeah, so we typically have the memory store 1 byte at a time. Yeah, because we want to be byte addressable. Yes, so as I said, when you want to read an instruction, I'm going to read 4 of these together to read one instruction. We good? Great. So now the next question is that I have 32 bits of PC, and let's say I have 1 kilobyte instruction memory. Which bits do I need to use? So I need to pick 10 bits out of this 32 bits. Which bits should I use and why? Anyone wants to answer? Yeah. Because you can do what? Well, why would that be useful? Uh-huh. Mm-hmm. Yeah. Mm-hmm. Yeah, you want to add something else? Mm-hmm. Mm-hmm. Big number. So yeah, so the comments is that it's usually easier to kind of have given that we always kind of like move around a particular PC, right? So I told you that you usually do PC plus 4, PC plus 4, or if you want to jump, you usually jump to a lower addresses. It's better to have addresses nearby each other. So it's usually we use the lower bits so that we can just regularly just add it by 4 and then go to the next one. If you, for example, use somewhere in the middle or the highest bits, then in order to go to the next address, I need to add the big number, or need to shift and then add, and all those things, which is more expensive. So we typically go with the lower significant bits, the first 10 bits or 12 bits and whatever, to address this memory. And then, of course, then the next question becomes that if I'm ignoring the rest of this bits, doesn't that mean that we're going to have some overlap? So essentially, this means that if the lower bits are all zeros, and then this bit is 1, versus if this bit is also 0 and this all bits are also 0, then these two are essentially pointing to the same location. And the answer to that is yes. They're going to point to the same location. And that's what we call the overlap or collision in the instruction memory. Later on, when we talk about virtual addresses, you're going to see how we fix this issue. But for now, just keep in mind that you have limited size of memory, unfortunately, which means that you cannot store more than 1 kilobyte of data. If you want to store more than 1 kilobyte of data, you need more memory. That's simple as that, right? So that's why you're going to have overlap if you have more data than what you're thinking you have, all right? Okay, so going back to here, and as I told you that we're going to store bytes, but we're going to read words. So we're going to read 4 of them together because we want the memory to be byte addressable. All right, so this is basically the first step that we talked about. We're going to fetch the instruction from the instruction memory by providing the lower bits of my PC to the instruction memory. There is some kind of logic going on inside the memory that one line becomes active, and there is some form of a multiplexing going on, and then we're going to read that data, okay? At this point, I'm going to have a 32-bit value, which is my instruction, okay? So now let's talk about this rest of the steps, okay? So let's talk about this operands that we want to load. And as I said, remember that there were 3 operands, okay? So let's talk about the immediates first, because the easiest one is the immediates. So the immediates, one thing to notice is that the immediates is already embedded inside the instruction. So I read the instructions that I have 32 bits. As you can see, the immediates are already inside that 32 bits. All I need to do is understanding which instruction is this and doing the proper kind of management and sign extension. So for example, R-type does not have any immediates. I-type has immediates at this top 12 bits. S-type and B-type and so on has at various different places. So what I need to do is that moving these things around, right, and then do the proper sign extension as well, okay? So what we're going to do is that we're going to have this unit called sign extension unit that I'm going to show you later that essentially does this for us. But just keep in mind that I don't need to do anything extra other than just reformatting the immediates for creating the correct immediate in my instruction. A more involved process is reading a register. Remember that I told you that reading a register is going to the register file and reading the data from it, okay? And remember I told you that at any given time, we might have at most two sources, okay? RS1 and RS2, okay? So the way that we're going to design a register file is that we're going to design it in such a way that I can read both registers at the same time. Because again, this is a design decision. This is a trade-off. We can read one at a time, but that means that the process of reading is going to be serialized. I need to first read the first one and then the second one. What I can do instead is that have what we call a 2-port register file, which we read 2 things at the same time. So here's what I'm going to do. I'm going to have read register 1 and read register 2. This is the numbers that we're going to provide. This is RS1 and RS2. And remember, there are 5 bits. Why there are 5 bits? Because we have 0 to 31 different registers, okay? So we're going to provide these 2 5 bits. And then what we're going to read is the actual values, okay? So this is the value that is stored in those registers. How many bits I'm going to get here? How many bits? Yeah, 32, right? So this is a 32-bit value. And this is also a 32-bit value, right? My registers are 32-bit. So I'm going to provide these 2 values here. This is RS1. This is a number between 0 to 31. This is RS2. This is a number between, again, 0 and 31. And then I'm going to read the corresponding registers after some delay. Remember, this is also a flip-flop, so it takes some time for me to read. There are two other things that we also have. Remember that you not just read from the register, you also write to the registers. So I provide these two other inputs to my register file. I provide write register. Write register is essentially my RD. And again, it's 5 bits because it's a number between 0 to 31. And I'm going to provide the data that I want to write to that register. Again, how many bits this should be? This is also 32 because I'm going to write to a register, so I need 32-bit data to write to the register. Okay? And for now, don't worry about this. This is my write enable, and it's controlled by the controller. That's why it's blue. So not all the time we're going to write to the registers. We're going to always write to the register only when this write enable is active. I'm going to later show you how we designed this part. But for now, register file is this, has 4 inputs and 2 outputs. The 4 inputs, the first 2 inputs are the RS1 and RS2. The third input is RD. The fourth input is the data for writing to the registers. And the outputs are the values that are stored in RS1 and RS2. And as I said, not all the time we're going to use all of these together. Sometimes we write, sometimes we read, sometimes we do all of them at the same time. Essentially, we designed it this way that we can do this in parallel. That's why we did it this way. We could have, for example, had just one input and one output. So essentially, we have just read data or write data, and then we have just one output here. This would mean that I need to serialize this activity. So I just read and then write, or just read one bit at a time, which is not efficient in terms of design. All right, let's answer some questions. Yeah, the question is, can we read and write at the same time? And the answer is yes. Yeah. Say it again. The question is, what is provided if you only have one register? So what we're going to show is that we're going to always just hardwire this to the part of the instruction. If your instruction is only, let's say, has one register and one immediate, you're going to essentially connect garbage to, you're going to provide garbage, and you're going to read garbage, and you're going to discard. So we're going to design it in such a way that if you read things and it's not relevant to us, we're going to discard it correctly. That's why we actually have write enable, because imagine that your register file, your instruction didn't have a write an RD, a destination register, and you're providing a data to that. You would write to arbitrary registers that you were not intended to. That's why we always control this with the write register. Yeah. Correct. So the question is that how do we set read-write? And the read-write is instruction dependent. Some instruction needs to be written and some not. When we design our controller, which is that blue unit, you're going to see how we actually set this. Yeah. The question is, if we get rid of the writes, if the read part is combinational, and the answer is yes. Yeah. The question is, if we want to write to a register, how do we know which data to write? So writing happens at the end of an instruction. So you need to execute it and do the ALU operation and all that things, and then when you have the data. So when we're going to show you the full data path, you will see that the writing happens kind of the end of the cycle. So in this kind of life cycles that I showed you, writing happens at this point. So you actually first execute and then write the updated data back. Does that make sense? Yes, exactly. So the reading happens at what we call the first cycle, the first half cycle of the instruction, and the writing happens at the second half of the instruction. And we're going to show you how we actually, so this time synchronization would be important, and we're going to show you how we do that. Yeah, question in the back. Yes, so the question is, when we are writing, we set which register we want to write to at the beginning. And remember, that was your RD already encoded into your instruction. So you already know which register to write to, but the actual data happens later in the instruction execution. Good observation. Final question. All right, so let's continue. All right, going back down. All right, so this is my register file. And as you can see, this is how we're going to connect. So remember I told you that location of RS1 and RS2, we want to be consistent. The reason for this is that then I can just basically hardwire things directly. So as you can see, bits between 15 to 19 is always RS1. So I'm going to connect that directly into my read reg 1. And then same thing for RS2. And I'm going to connect that into this data. And then same thing for RD. I'm going to connect that into this data, right? And again, you might wonder that, oh, no, that's not true. For example, in this case, this is immediate and so on. Again, we're going to connect this for some particular instruction. This is not relevant. We are providing irrelevant data, but nothing bad will happen because we have the controllers to tell us which one is relevant and which one is not relevant. That's why we have data path and controller. We cannot design this processor only with the data path because we need to do different things for different instructions. So we need some form of a controller for this. Okay? So as I said, this is for RS2, this is for RD. So we're going to connect these guys then together. All right? So now let's actually create some form of a big picture. So remember I told you that we provide the PC. The PC gonna, let's say, for example, the lower 10 bits gonna be connected. Then I'm gonna read 32 bits. This is how I'm gonna, so this is like a 32-bit lines. Then I'm gonna literally hardwire it this way to the register file. So I'm gonna connect 15 to 19 to read reg 1. I'm gonna connect 20 to 24 to RD2, RS2, sorry. And I'm going to connect 7 to 11 to write the RD, okay? So this is literally just hardwiring connection between the register file and output of the instruction memory, okay? Yeah. The question is that is the instruction memory is also registered? We typically do this combinationally. So we provide the address. We wait for, let's say, some time, and the output would be available. You don't need to register it anyway. But later, we're going to show you the pipeline design. So then that way, then this will be written into a register, and then we're going to read from that register. Okay? But for now, there is no pipeline in between, which means that I provide the address. I'll wait for some time for the data to be read. And then that wire will be connected directly to the register file. And again, register file will read things combinationally. So it's kind of like just a big delay of providing the PC, reading the data off of the instruction memory, reading data off of the register file. All of these things, like from here to here, happens all in one clock cycle with some delay. All right. So let's talk about the next step. And then that is, so we have the immediates. The immediates are easy, right? The immediates are essentially already inside the instruction. We just need to kind of like move them around. We talk also about the register and how we use register file to read that. Let's talk about the reading data memory, because that was the third operand that we need to be worried about, right? How do we do that? Data memory, as I said, so data memory very similar to instruction memory. The only difference is that for data memory, we have address and we have read data, but we also have write data because we can also store things to the data memory. We don't need to store things into the instruction memory. That's why we don't have write data to the instruction memory, but we need to write things to the data memory. So that's why we have this. And then again, one thing that you have to pay attention to is that we have memread and memwrite for data memory as well. Why do we need memwrite? I'm going to later show you why we need both read and write enables in this particular case. And as I said, for now, we assume that data and instructions are two separate things. Later on, we're going to combine them together. Okay? Okay. So now the question is that how do I choose between the immediate registers and operand and the memory? Let's have a quick break. We're going to come back to this and we're going to answer this question. All right, let's continue. So now we need to decide which operand to load, and then also some of you pointed out already that another problem that we have is in some cases we are reading something that we're not even using, right? So for example, some instruction doesn't even have RS2, but we are still reading RS2 and so on and so forth. So how do we control this? Okay, we control this using a controller. Okay, controller is literally a unit inside my CPU, which has this kind of like orchestration controlling of various different types. Okay, so as I said, our design of a CPU has two main parts that I already showed you. It has a data path and a controller. The data path is basically a collection of these functional units that is used to process the data, to create the new data, to store the new data, and all those things. And the controller that is a unit that kind of check and manage this data flow. This what instruction should do what, which unit should be active, what should we read, and what should we write, and so on and so forth. Okay. This is what, as I said before, this is what we call a store program or one Neumann model. Essentially, you can think about a one Neumann computer as a computer that gets some inputs, produce some outputs, and underneath it has two main units. It has a CPU and a memory. The CPU has also two subunits, has a data path and a controller. That's the simplest way that we can design a computer. Okay, and the data path, a CPU and a memory. Inside the CPU, we have a data path and a controller. Okay. So, and as I said, these controllers are you're going to see these blue lines in many different places in our data path. And this is where the controllers comes into the play, right? So it's control things. For example, checks whether we need to read from the memory, write to the memory, write to the registers, and so on and so forth. Okay. So how do we actually use the controller? If you remember, excuse me. The controller was, our instructions had this thing called opcode, right? And the func3 and func7. And that was the key point to decide which instruction does what, okay? So in order to design the controller, what we do is that once we read the instruction, we have this 32-bit, we're going to pass that into the controller so that the controller takes the instruction and make the decisions. So essentially, the design of the controller is this. It takes the instruction as the input, then it produces these control signals, various different control signals, like 10 different control signals we're going to produce in our design based on the instruction. Okay? How do we build a controller? So, for example, we have different R-type instruction and I-type instruction and so on and so forth. Each one needs to do different things. What's the best way of designing a controller for this? What's the logical way of designing this? And you probably, again, have seen this in your past classes. We're going to use this thing called finite state machines, or FSMs, okay? The finite state machine is essentially designing this system as multiple steps. In each step, we're going to produce some outputs to the system, and that's how we're going to create these signals, okay? So for those of you who are not familiar with what is an FSM, FSM is a mathematical model of a computation, right? If you have different operations and you need to decide at each different point of that computation what you need to do, you use different states, and then you have a transition between those states, okay? So at any given point, we always add one and only one state, right? And then we have this kind of different ways of transitioning from one state to another in order to create the system that we want to have. For example, we have something like the simplest FSM we can assume, let's say, has 3 different states. There is some condition that if the condition, let's say we start from state 1, if the condition is true, we go to state 2. If the condition is true, we go to state 3, and maybe we revert back to state 1. Sometimes we may need to stay in one state, so on and so forth. Sometimes we can jump from one state to another state or skip some states and so on and so forth. The design of an FSM, it depends on the problem that you're trying to solve. We're going to particularly design an FSM for our problem, which is a CPU design, okay? But the basics are exactly the same as any other FSM that you have ever created, okay? So you need some states. You need to define those states. You need to define the condition from transitioning from one state to another. Sometimes you need to connect from one state to multiple states. You always just go to the next state and so on and so forth. And then in each state, you need to provide some output. So you create some control signals at any given state, okay? This is how we're going to design this, all right? For the processor, think about this as a giant state machine, right? Many states, many different signals, and so on and so forth. The more complex your processor is, the more complex your FSM becomes, okay? We actually, let me see if I have, yeah. So this is kind of like to just give you a view of how the FSM for our processor looks like. It looks something like this. As you can see, those like, within each kind of circle, we have this different things equal to this. These are my control signals. These are those blue signals that I'm showing you on that picture at the beginning. So you see that, for example, in the fetch state, we have like PC source is equal to 0, or I don't know, PC write is equal to 1, and so on and so forth. We're going to talk about each one by one. But generally, that's the idea. And then you can see, for example, from decode, we can go to the branch type instructions. We can go to R type instructions. We can go to the load word instruction, and so on and so forth. So things branch out depending on the opcode, right? That's how we're going to decide whether the RS2, for example, that we read was useful or not. We're going to decide based on the opcode. We're going to see that, oh, this is an S-type instruction. Doesn't need RS2, for example. So we can ignore that and move on, okay? So for now, don't worry about the specifics of this. I'm going to get back to this once I finish my data path. I'm going to first finish the data path all the way through. Then I'm going to come back to the controller and talk about these different states and every single signal that we generate in each state, okay? So going back up, as I said, FSM for a processor would be a giant FSM machine. And then again, if you remember the life cycle of instructions that I told you that we fetch and then decode and then execute and then go to the next state, that's basically what we do, right? So we start with like reading instruction and decoding them. The next state is kind of like, go through some process of executing and reading memory and all those things. And then finally, we update the PC and go back to state 1, which is fetching the next instruction, okay? And as I said, we repeat this process over and over. So we're going to go all the way down, then come back up to the first initial state, and then repeat this process over and over again, okay? One thing that you're going to see in this class is, depending on how you switch between the states, you're going to have different designs. So for example, if I have, let's say, 5 different states, okay, if I do this all in one cycle, so essentially in one cycle, I fetch the instructions, I execute them, and then I kind of like, update the PC and save the results PC and then go back. If I do all of these things in one cycle, we call this a single cycle machine, which means that every clock cycle, I run only one instructions, okay? There is an alternative to this, is that each state will take a different cycle. This is what we call a multi-cycle machine, right? So for example, one instruction might take 1 cycle, one instruction might take 3 cycles, depending on how many states do we need to traverse. And finally, the design that we mostly going to use is what we call a pipeline machine, which essentially every clock cycle would be one particular state, and all the instructions are going to go exactly through the same process. For now, we're going to focus on what we call a single cycle machine, which means that we're going to have internal state, but traversing from the beginning of the first state all the way to the end state and coming back to the same state that we had only takes one cycle. So clock comes, we do all this process, we go back to the state one, and then the next clock comes, okay? This is what we call single cycle machine. So let's design this single cycle machine, and as I said, for now, ignore this, but we're going to come back to this. All right, so where are we? We were talking about this, and we want to design this. I already talked about the first one, which is fetching an instruction. I told you that then we talked about the second part, that is reading the operands. We see that we have different types of operands. We hardwire them somehow that we can read the proper values if we need to. But the problem that we ran into was we don't know which one, and different instructions needs different types of operands. And then that's where we introduce a controller. And the controller basically understands the instruction and provide this kind of control signals to us. We designed this using an FSM. An FSM have multiple different states. In our current design, we traverse all the states in one cycle. So we basically do everything required for one instruction in just one cycle, and we call this single cycle design. Okay? So let's continue this. So we are at here. We need to do this one, and this one. All right? Okay. So this is kind of what we have so far. We have the PC connected to the instruction memory. I said that the number of bits here depends on the size. Let's say 10. We read 32-bit instruction. We connect relevant bits to the register file. We also feed this into the controller. Okay? Here's what we're going to do from this point on. Okay? I'm going to focus only on 10 instructions. Okay? Remember, I showed you this big giant table of all the instructions that we're going to learn in this class. But in order to build my rest of my data path, I'm going to just focus on 10 instructions. The reason for this is that makes the design simpler, because every instruction might require additional things that we need to add to the processor. So we're going to just focus on this 10 instructions for now. Later on, when we are talking in your quizzes and homeworks, we're going to, let's say, for example, add support for this instruction, or we're going to create this custom instruction, add support to that. You're going to understand how we're going to do that. But for now, we're just going to focus on these 10 instructions because make things much simpler. The instructions that we're going to focus on are 4 R-type instructions, AND, SUB, AND, and OR. We're going to focus on 2 memory instructions, load word and store word. We're not going to focus on store bytes or store byte unsigned for now, just yet. And then we're going to have just 1 control flow instruction, and that is branch equal. That's the only thing that we're going to focus. So only these 10 instructions. We're going to also have 3 immediate instructions, add-I, AND-I, and OR-I. Okay? So these 4, then these 2, 6, 7, 8, 9, and 10. These are the 10 instructions we're gonna focus on. Your project's going to be also these 10 instructions, maybe like 1 or 2 more that I'm usually change from one year to another. So let's see how we build this, okay? And to kind of remind you, this is the machine code for these 10 instructions only, okay? So you can see that some of them has RD here, some of them don't. All of them have the same exact place for the opcode. They have different func3, and then RS1 all of them has. Some of them does have RS2, some of them don't. And then some of them have func7, some of them don't. Some of them have different places for the immediates. Some of them are very clear where the immediates are. Okay? Let's continue. As I said, this is the things that I already said. So we're going to build this based on what I showed you for that 10 instructions. So this is the data path that we're going to generate for that 10 instructions. Again, for example, if I wanted to add let's say store bytes, I needed to change this part a little bit. So that's why for now, I'm just assuming that I'm only supporting that 10 instructions, okay? So let's go over this design together. We already covered part of it. So we covered this part, we covered this part, we covered this part. Let's talk about this rest of this design here, all right? So this was the data path. So the first thing we're going to do is that we're going to create our next PC. That's a very simple thing to do. So we're going to do it now. All right? So how do we create our next PC? we're going to take the PC, okay? I'm going to put an adder that basically all it does is that it adds a hardwire 4 to the PC, and I'm going to produce and connect that results back to the PC, okay? And remember, this is a clocked signal, which means that at the next positive edge of the clock, the value of next PC going to be stored in PC, okay? So this is what we call PC. This is what we call next PC, okay? So my PC, I'm going to add it to 4. I'm going to put it back to the connect it back to the PC. Next time the positive edge comes, PC becomes next PC, which in this case is PC plus 4. So I'm going to just for now do PC plus 4, PC plus 4. You other question? Uh-huh. Uh-huh. So the question is that we in the past we said that we need to make sure that the lower 2 bits of the PC should be always equal to 0. Here we don't do that check. Why we don't do that? Because we are assuming that the PC already starts with the correct value. So to assume this, that if the PC starts with the correct value, whenever you add 4 to it, it stays, multiple of 4. So I don't need to do extra checks just yet. But we're going to actually add that check later. So you're going to actually see that when we're doing the arbitrary PC. But for now, since I'm just doing PC plus 4, PC plus 4, assuming that PC starts with the correct PC that is multiple of 4, I don't need to be worried about it because I'll always add just 4 to it. Okay? So having an adder, and by the way, this is how we're going to show you an ALU operation or adder. It's kind of like this design that we add. And in this case, it's just add. It's just doing very simple add, nothing else. And then I'm showing you 4 here. We can create 4 different ways. You can takes 2 bits from the VDD and 2 bits from the ground, and you can create 4. There are different ways that you can create 4. Okay? All right. So this is kind of the updated version of what I had. So I have my PC. Now I have the kind of the upper side of my data path. I have PC plus 4. There's something going on that I haven't shown you here just yet because there is a branch equal instruction. So next PC is not always PC plus 4. It depends on the branch. That's why I'm not showing you here. But that's kind of like a more completed design. Okay. So now let's talk about the next important thing, and that is your ALU. Okay. So ALU, again, we show it similar to the add. The difference is that ALU could be different operations. Remember, we can support XOR and sub and 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 so on in that 10 instruction that we have. So what is the ALU? What it takes? So it takes 2 inputs, okay? And remember, these 2 inputs could be either 2 registers or 1 register and 1 immediate. So there are 2 possibilities. But in both cases, we take 32-bit data, okay? So the ALU takes 2 32-bit data, okay, and produce what we call the ALU result. And again, this value is also 32-bit, right? But since we have different operations, we might have an XOR, an OR, or and so on and so forth, we need to have a control signal, okay? And this control signal is what we call ALU operation or ALU op, okay? Why is it 4 bits? Because we need log 2 of the number of operations that we want to support. That's why it's 4-bit. Since we are only supporting 10, less than 4 would have been enough. The reason that we are doing 4 is that assuming that you want to extend it to all the instructions that we learned in this class, then you would have need 4, okay? So the way that we're going to cover this is that we're assuming that you can support many different ALU operations. That's why it's 4-bit. But you technically could have arbitrary operations for that 10 bits that we, this 10 different instructions, and you technically would have need less, okay? There's also another output for ALU, and that is called 0. For now, don't worry about this. For just a quick kind of summary of what it does is that this is a 1-bit flag, just 1 bit, that is equal to 1 when the results of the operation is equal to 0. And the reason that we need this is for something like branch equal, we will subtract the 2 registers from each other, and if it's equal to 0, this 0 becomes 1. So it will be used for the branch instructions and some other operations. For now, don't worry about it. So essentially, all you need to know for now is that you have a 32-bit input, two 32-bit inputs, one of them registers, the other one either register or immediate. We have an ALU operation that decides what to do, and it produces a 32-bit result. Okay? All right, so here's what we're going to do. So now we're going to connect the register file to the ALU. All right? So we're going to do it this way. So we're going to first connect the RS1 data directly to the ALU. But then we have this problem that I told you that in some cases, the input to the ALU is RS2. In some other cases, the input to the ALU is immediate. Okay? So how do we fix this issue? We're going to introduce this multiplexer. And this multiplexer takes two inputs. It takes the data from RS2, and then it takes the data from the immediate generator. Okay? This immediate generator, by the way, is the one that takes the entire instruction and move things around in order to produce the correct 32-bit data. Okay? How does it do that? Takes the full 32-bit. It has a giant kind of like a lookup table that for a given instruction, it knows which 32 bits to use. Like, move things around, produce the 32-bit for you, and also does the sign extension. So here we do the kind of reshuffling and the sign extension together. So the output of this is a 32-bit value that is correctly shuffled. It's kind of like correct bits, also nicely sign extended and all. Okay? Later on, we're going to talk about how do we design this. But for now, just assume that takes the 32-bit instruction, magically creates the immediate that you want. Okay? So we have the 32-bit immediate here. We have the 32-bit RS2 here. We need to decide which one to use. That's where the controller comes handy. Okay? We're going to introduce this control signal called ALU source. And as the name suggests, it picks which source we're going to use. If it's equal to 0, okay? If it's equal to 0, we're going to select RS2. So this one will be connected. If it's equal to 1, we're going to we're going to connect immediates to this, okay? So again, from the ALU point of view, we don't know which inputs we get. We always get two 32-bit. But we're going to design this system with this ALU source such that if the instruction is an R-type instruction, which means that it requires two registers, ALU source will be equal to 0. If it's an I-type instruction, or if it's a memory instruction like a load or store, it connects the immediates to the ALU, to the inputs of the ALU. Okay? And then it also provides the right ALU operation. So for example, if you need to add or subtract or AND or and so on and so forth. Okay? Question? Repeat again. The question is, what does immediate gen do for R-type instruction? Nothing. So essentially, again, creates a garbage, but it doesn't matter, right? For R-type instruction, we're going to create the garbage here, but we're never going to read it because for R-type instruction, it needs to use RS1 and RS2. Yeah. I didn't catch the question. Say it again. Uh-huh. So the question is that if you have an operation that this one is 2 and this one is 2 and the operation is sub, what happens to these two numbers? So this one will be equal to 0, but it will be a 32-bit number. This one will be equal to 1 and it's only 1 bit. Okay? Any other questions? Cool. All right. So let's continue. So as I said, this is 32-bit. I'm kind of providing information of how do we do the immediate generation. So as you see, 6-bit opcode is deciding whether you have load instruction or store instructions. You can decide how to multiplex and so on and so forth. I'm going to actually give you the design of the immediate generator as like a homework question so you can see. But generally, the idea is that based on the opcode, you know exactly where your immediate bits are. So you can have different options for your immediate. You have a multiplexer. Based on the opcode, you select which one of these immediates you're going to generate, right? So, for example, remember that if I go back up, your immediates was kind of weird, right? So for some instructions, you didn't have immediates. For some instructions, you have nice immediates, like 12 bits, bunched together. For LW is also the same, but for SW, you have kind of like your immediates looks like this. And then for BEQ, your immediates looks like this. So essentially what I'm going to do is that I'm going to have an immediate R, immediate I, immediate S, and then immediate B. I'm going to create these 4 immediates based on this, and then I'm going to select which one I want to generate as my final immediate based on the opcode. Okay? Very simple way to create this. How do I do this? Essentially, again, I'm going to, for example, for this one, I need to reshuffle bits, right? So I need to kind of like, I need to connect these 3 bits as the beginning. I need to add a 0 myself. Then I need to connect these bits here. Then I need to take this bit and put it here. And then I need to take this bit and put it here. That would be my 12-bit. That's how I'm going to create this 12-bit, right? And I need to then feed this into a sign extension to get a 32-bit. And that would be my immediate B, right? So I'm going to shuffle first, sign extend next, and then multiplex at the end. Question? The question is, why do we do this like this? Because later on when we design the branch predictor, you're going to see that the sign bit is important. The most significant bit is also very important. So this is, again, for making those designs simplified. For now, it's a little bit more headache for us to create the immediate generation, but later on, you're going to see that the branch predictor will benefit from this. Yeah. Yes, the immediate generator is literally a combinational logic of multiple wires kind of like shuffled around, and the multiplexer in the end that selects which one to go. There's nothing, intelligent about it. Yeah. For this particular case, yes. For the immediates, right? So the question is these 2 bits kind of tells you what sort of immediates you're going to use, and it's kind of actually I think these last 3 bits is actually what you're going to use, but you can actually see the logic and you will decide for yourself. Yeah. Probably again M1 M51 you had the logic minimization, you had the tables and all those things. This is what you're going to use it that way. Yeah. Uh-huh. Correct. So the question is, if I want to write an assembly code, the maximum that I can provide is 12 bits. The answer is yes for this. But remember, we had also that LUI thing, which has 12 to 31. So you combination of this and that, you're going to have a 32-bit if you want to. All right, so going back down. So I'm going to connect this to, I'm going to generate my immediate generator, and this would be a 32-bit value. And as I said, this is the multiplexer that I'm going to use, and we call this ALU source multiplexer that decide whether I'm feeding immediate or the register number 2, RS2, to my ALU. Okay? Let's add the memory to this mix as well. So I'm going to add the memory here. Why am I adding the memory after the ALU? The reason for it is that I want to generate the address of the memory from the ALU, okay? And so 2 options that I had that I could do this, right? So I need to generate the address. And remember, the address, the way that we generate the address was we take the base register, right? So how was like LW was something like this, right? So RD, RS1, and immediate, right? So I need to take the RS1. I need to read the register file. Obviously, I cannot compute the address of the memory before the register file. That's given because I need to first read the value of the register. But I then need to add register this RS1 with the immediate, okay? So I need an adder here, okay? So two options I have. I can have a dedicated adder for the memory addresses, the same way that I did for PC+4. In that case, I could have had, basically, I read this, I connect these two to an adder, and connect that to the memory. That's one option. The other option that we like more to kind of save the adders, because adder comes with a cost that we don't want, I'm going to use the ALU for using that adder. So I'm going to use the ALU's adder for generating the address, okay? So essentially what happens for the memory is that I'm essentially connecting RS1, and then in this case, the immediate to the ALU. I'm going to add, and I'm going to get that result and connect it to the address, okay? This is how I'm going to generate the address, right? What should be the right data to the memory? If this is a store, I still need the address, so I still connect this. But the value that I'm going to provide, remember it was RS2, right? So I'm going to connect RS2 to the right data, okay? And then I'm going to have the controllers here as well. The next thing I'm going to add is this thing here. And as you can see, what it gets is this value here, the value of ALU, and the value of the memory. And then if you follow this, you will see that this is connected all the way to write data of the register. Why are we doing this? So remember, if I have an R-type instruction and I-type instructions, like add or and I and so on and so forth, I take one register and one register on immediate, I do some operations, and I store that result back to RD, okay? This is the value that is coming from. So from here, goes to here, goes to here, okay? This is all ALU based, okay? But let's say this is a load word instruction, okay? If it's a load word instruction, load word takes this address, reads this value, and write this value to RD, right? So this means that this value going to be connected from here to here to here, okay? So this is why we have what we call a mem to reg multiplexer. Basically decide the value that we want to write to our register file. Is it coming from the memory? In other words, if this is a load word instruction, or is it coming from the ALU, which is this is an I-type instruction or R-type instruction, okay? And not in all cases we are writing to the register file. So in some cases we provide garbage here, but we control it with not writing to the register. So for example, for store word, we are not writing anything to the register. We are writing it to the memory. So we don't need to write anything to the register. Although either of these two can be connected, I'm not going to write it to this register because the read write is equal to 0. Okay? So again, taking a step back. So this part we already discussed. What we are adding now is this part. I told you that one major design decision that I make here is that I'm not going to add a dedicated adder for computing the address. What I'm going to do instead is reusing the ALU the ALU itself and the adder within the ALU. So I'm going to connect the output of my ALU to the address. Then I have a bunch of complication that they need to figure out. Basically, the main complication is that what should be written to the register file? And I have two options. Either I need to write things from the memory, or I need to write things from the results of the ALU. And that's what this multiplexer does. Any questions? Great. So this is quite complicated as we add more things to it, right? So there are a bunch of different control registers and kind of like different parts of the design is completed. The way to understand this is that you go back after this lecture, you kind of rewatch this hopefully again. or you just try to kind of mix, like put the whole design in front of yourself and to understand why we have this certain decision. Everything there is there for a reason, right? So you have to understand that. And the second thing that you will see is that we're going to design this in C. So you're going to code this actual design in C. That's where you're going to actually understand all of these things much better. So it will take some time for you to this to be resolved. Yeah. Correct. So the question is that this kind of design is only triggered for load word and store word, and the answer is yes. In like a massive actual generic design, we're gonna have store bytes and load byte and unsigned and so on and so forth. So your controller will be slightly more involved. All right. Uh, ALU source, mem to reg, storing data. All right. So last thing before I let you go is branch, okay? So the last thing I want to add is branching. Remember, we also had branch equal, okay? So remember, what branch equal does is that it checks whether RS1 is equal to RS2. If it is, then PC should be equal to PC plus offset, right? What is that offset? This is the immediate value. And the current PC, we just add the immediate to the PC, okay? So here, this is what we're going to do. We're going to get the PC value that we get from the data path. We're going to add it to, we're going to have an adder for the PC because I cannot reuse this ALU here. Why? Because this ALU is used to check the control logic. We need to check RS1 and RS2. So RS1 is here, RS2 is here. I'm going to basically subtract these two from each other. If 0 flag is equal to 1, it means that these two values are equal. So this is where we're going to check the condition. I also need to compute the branch target, where I'm jumping to, right? And where I'm jumping to is that it takes the PC, adds it with the offset, which is the immediate. Okay, so the immediate from the immediate generator comes here. Remember, we had to left shift by 1. We had to zero out the first bit, right? Because we don't want to jump to arbitrary locations. This is where that happens. So we're going to get this value that is like the lower significant bit is zeroed out. Then we're going to add these two numbers together, and that would be my branch target. Okay? And now the last thing is that I have my branch target. I have my branch condition. Now I need to decide whether this branch should be taken or not, because not all the time the branch should be taken. So I'm going to add two things to my design, okay? I'm going to add this PC source here that essentially decides between whether or not I should take PC plus 4 or I should take PC plus offset, okay? That's one thing I'm going to do, that to decide between which one is taken. The second thing is I need to basically decide whether or not this branch is taken. And this is the value that I'm going to get from 0, and I'm going to somehow put it here. I'm going to later talk about how we're going to do that. But essentially, that will fed into the controller, and then the controller going to decide the PC source. So PC source is based on two things, whether or not this is a branch instruction and whether or not 0 is equal to 1. Okay? These two together will create this PC source. But generally, this is how we're going to decide between what is the next PC. We're going to get the immediate value, PC value, add them together. This is your PC plus offset. This is PC plus 4. And either of these two will be selected based on this PC source. Yeah, final question. Question is, why is shift of 1? I remember I told you that there are some 16 bits instructions in RISC-V that we need to support. So not all the instructions are 4 bytes. Some of them are 2 bytes. We're not going to cover them in this class, but we have to be able to support those for in general. Again, if I only want to support these 10 instructions, this left by 2 was totally fine. All right, any final questions? Yeah. Can you come here and ask a question?
address you would jump to, is that calculated every time?